In this video, I'm going to show you the best way to create a wideband filter. Now, of course, the term wide is relative, but in this case, I'm going to design a filter that will pass through frequencies between 10 Hz and 60 Hz, and you will see that this is a relatively wideband filter. You will also soon learn why I call this a two-stage filter as opposed to just a bandpass filter. Okay, so I'm going to create a filter, goes from 10 to 60 Hertz. The transition width, so the symmetric transition width for both sides is going to be 10%. The sampling rate will be a little over 2 kilohertz, and we'll start with a filter order of 8, a factor of 8 times the lower bound. And then I'm going to create this filter kernel using the FIR-LS function. So this is the same shape and set of frequencies that I have described in previous videos. Then I plot the time domain filter kernel and the frequency domain filter kernel. So let's have a look. Here's the time domain. This already looks a little bit weird in my opinion. And here, when you see the spectral shape, you know immediately that this is an awful filter. You do not want to apply this filter to your data. It's going to amplify features in your data that are outside the range of the filter that you specified. So you can try taking a few minutes to change these things. You can try changing the filter order or the transition widths. You will find that if you really want to keep this range of filters, 10 to 60 Hertz, it's going to be really hard to create a nice filter. So the much better approach is to filter twice. First, you apply a high-pass filter at 10 Hertz, and then in a separate filtering step, you apply a low-pass filter at 60 Hertz. And that is why I call this a two-stage filter. Okay, so let me show you what that looks like. We're going to generate just some random numbers, just some white noise, so we have something to filter. And you can see what I'm doing here. I'm going to create a high-pass filter first, and then I create a low-pass filter. So the high-pass filter I'm doing with FIR1, and then here I'm also extracting its amplitude spectrum or power spectrum, so you can see that's plotted, that's going to appear down here. Here I apply reflection and the zero phase shift filter. Again, this is nothing new. This is all code you've seen in previous videos. And here is the second step. So this was the first step, applying a high-pass filter. And the second step is going to repeat this for a low-pass filter. So again, this is a low-pass filter at the upper bound. And one of the nice things about separating this for the high-pass stage and the low-pass stage is you can set the order to be different. So here I want the order to be higher for the low-pass filter compared to what I set it for the low-pass filter. The high-pass filter. And then the rest of this code is basically the same. The important thing to notice here is that I'm no longer filtering the original signal, or it's called noise, but the original variable. Instead, I'm filtering the already filtered signal. So you take the filtered signal and then you filter it again. And this line of code here is just a quick reminder that if you have the signal processing toolbox, you can just use this line, filt, and that will replace these 5 lines of code. All right, so let me run this and we can inspect this filter. So here you see the black line shows the high-pass filter, the red line shows the low-pass filter. And it doesn't matter that these are in 2 separate filters and the data are filtered in 2 separate steps. The result will be comparable to if this filter had looked really good. All right, and then just show you the results of the filter. So then you see here's in the time domain, the blue line is just random noise, and the orange line is the bandpass filtered version of the noise. And here in the spectrum, you see, not surprisingly, that you attenuate all the frequencies below 10 Hertz and above 60 Hertz.